Hello, my name is Alberto Marquez. Welcome to this video on quality improvement. Particularly, we're going to discuss control charts, and we're going to see an overview of how control chart works, what's their philosophy, how they are implemented. We will then work particularly with the discussion on control chart for variables, then for attributes, and finally we will have a discussion on the utilization of capability indexes like CP and CPK. So let's go. The objectives of this module are to explain the fundamental of control charts, to explain the fundamental of control charts for variables, explain the fundamentals of control charts for attributes, and explain the fundamentals of capability concepts. In order to do this, we're going to go into some of the details of how to construct control charts and the different type of performance indicators for these control charts. A control chart is a tool that is used to measure the performance of a process or the behavior in some key variables or parameters in the measurement of the quality of a product. Usually what we do is we take a sample, and this sample is larger than 1, and we take some measurements, and we usually compute some measure of central tendency, usually the average, and also measures of dispersion like the range or the standard deviation. Due to the central limit theorem, what we would expect to see is that the mean of the sample would behave in a almost normally distributed behavior, or near normally distributed. And because of that, we make some assumptions regarding the likelihood of where these sample means would fall. So here you can see a transposition of the normal standard deviation mixed with how we would represent the control chart. And you see we have an upper and lower limit at 3 sigma. That means that the probability of going beyond 3 sigma is less than 0.14%. And together both tails, or the probability of falling in on either side beyond the limits, is 0.27%. And so that's a not very likely event, and the logic is, if that happens, then there must be some special cause that generated this event, and then we must stop the process and check what would be a possible explanation why we obtained such a measurement. Now, there is an alpha error about it, which means that it could be that there is nothing wrong with the process and still we obtain a point like that, but it's very unlikely. The reason why we construct control charts is to separate the common causes of variation and the special causes of variation. Here we have a layout of what would happen with time in terms of what happened with these control charts. If everything is behaving correctly, we may have the sustained mean, that is, we remain with the same mean and same standard deviation. Even in those conditions, sometimes we can see that there is the process out of control when there is some randomness, and we will discuss those instances. In this other part of the graph, we can see that the standard deviation is changing. It could go being reduced, or it could increment. In general, for the processes, when the standard deviation reduces, is better because that increases the repeatability of the process and other performance indicators like the CP and the CPK, which we will discuss later. In general, we do not want any process to increase its variability, like it's shown in the high part of this diagram. Here at the bottom right, you see a situation in which the distribution has a shift to the right, and therefore it is out of control. So we want to avoid situations in which either the variance or the variability and or the mean are changing. Those are situations in which the process or the product is not in control. Now, being in control is not the same as being in compliance. We also are going to discuss that. Some of the situations in which we could find that the process is out of control, even though there is no changes in the mean, is, for instance, when it's correlated and still stationary. When it's correlated and stationary, it means that it still fluctuates around the same mean, but it doesn't do it randomly. There is some pattern, maybe oscillation that is depicted in the image, in which it seems like there is some inner cause to project this type of pattern. And there could be different type of patterns, but the main thing is, if it's not random, it means there is some other cause, and we need to find what it is. And if we can eliminate it, then therefore we could probably reduce the variability of the process without changing the mean. There are other situations which the process is not stationary, and everything that has a trend, either to increase or decrease the key performance measure or the key variable, it's considered non-stationary. Of course, we have issues when we obtain data points that are out of the control limits, and there are other non-random behaviors, like, for instance, you could have too many points on one side, or maybe this would also be correlated if you have 1 point above, 1 point below, 1 point above, 1 point below consistently. That is not random, and that would call for action to see what is really happening. From the human perspective, it's hard to pick up all these events, but with the advent of artificial intelligence and sophisticated statistical techniques, this is done easier now, because we are used to stream data into computers, and computers can predict easily or identify these patterns. Some important concepts that we need to understand regarding control charts are the average run length, which is the expected run length from the probability point of view. It is not a definitive run length. There will be runs that are longer than that, or maybe shorter than that, but in the long run, that's what we would expect to see. We have the average time to signal, which is how long it happens in terms of time, and that depends on the frequency of the sampling, because we are given the opportunity, maybe more frequently, for to obtain a stopping signal, and therefore we would stop, or would expect to stop every so often. And that average time to signal is measured in time compared to the average run length, which is measured in the number of samples. So if you have, say, for instance, 2 samples per day, then and the average run length is 400, then the average time to signal will be 200 days. We have different stopping rules that can be implemented, and that depends on how much we want to be sensible to changes in the mean. If we implement more rules, we very likely will have higher chances for stopping the process, and maybe stopping the process to verify if it's correct when we shouldn't have stopped it, which is an alpha error. It can be costly. So it is important to understand that there is a trade-off. If we don't stop when we should, that's a error type 1 with probability beta, and that is, we are incurring the cost of quality in that we are producing, we may be producing product that is not in compliance. At least there is a signal, but we may not realize it. On the other hand, if we fall into error type 1, we will stop the process when we shouldn't have stopped the process, and because of that, we incur in some cost of stopping the production line, etc. So these stopping rules can be of diverse nature, and we're going to explore a little bit more on detail how to use them to determine their impact on the behavior of our sampling process, and consequently on our control charts. One of the things that we want to do with these control charts is to establish a mechanism to identify special causes, and we can do this if we group our samples by rational subgroups. That means that maybe we can group the performance of one machine compared to the performance of another machine, as opposed to mixing all of them together. And if the samples of each one of the machines is different, then we can perceive that there is a clear distinction between the performance of the machines. That usually is the case, as much as is the case with using the same machine and changing from the first shift to the second shift to the last shift during the day. That also creates changes, and there are changes due to changes from one product to the next one. So the main idea is to be smart about how we group the information in the control charts in such a way that we can identify easier the potential sources of variation. It may be that it's a personnel that is not trained, it may be that a machine needs maintenance, or maybe some tooling needs to be renewed, and there is no recipe on exactly how to do it. It all depends on the nature of the process and the variables that we're measuring. Another important concept is the phase 1 and phase 2 in these control charts. Phase 1 is used to go back in time based on previous samples and identify the potential causes of variation, and in such a way that we filter out the changes and or the special causes, and if we manage to reduce those special causes, then we have a process that it's performing in accordance to what the process is capable, given the nature of the tools, the nature of the manufacturing process, the nature of the training of the personnel we have, etc. In the phase 2, once the process has been established as in statistical control, then we use phase 2 to monitor. We just want to keep the performance of the system consistent, at least. Of course, there is always opportunities for improvement. We want to get closer to the target in terms of the key performance measure. If it's the defective, we want to reduce the number of defectives. And more than anything, we want to reduce variance. So remember, that's our definition of quality, and that's what we will be focusing on, reducing the variance. The average run length depends on the conditions of that we have and the rules that we implement. The average run length, in case that we are in control, depend on the probability of assuming that we are not in control and we will have to stop the process. So the likelihood of that to happen is alpha, that is the probability of we stopping when we're in control, and we probably shouldn't, but we have to because we find maybe that one of the points fall out of the control limits, and then therefore we need to stop the process. Alternatively, when we are out of control, maybe due to a change in the mean, that would mean that the probability of us detecting that there is a change is 1 minus beta. Beta would be the probability of falling in error type 2. Error type 2 is when we do not realize that there was a change in the mean. So 1 minus beta is the probability of us detecting that problem, and that's when we would stop. So the number of times that we would have to take samples before we realize there was a change is computed as 1 over 1 minus beta. The last equation presented in this slide is when you have several rules that can apply. Each one of these rules have an independent or a relatively independent error type 1 due to the nature of the rule. And then if we have implemented many of these rules, the only way to stop or the only way that the run is not stopped is if none of these rules happen. So what we have here is the symbol pi represents the product and is the product of 1 minus alpha. 1 minus alpha would be the probability of not falling into error type 1. So, and the multiplications for independent events represents the joint probability of such events. So in this case is the probability that we do not fall in error type 1 in neither of all the potential rules, because it only takes one rule to call into action to stop the run for us to stop. So we need all of them not to send the stop signal, and 1 minus that, 1 minus all these multiplication would be the total probability of finding at least one of the rules to be sending notification stop. We're going to talk about that a little bit more in detail in the next slides. Here you have some of the most popular stopping rules. The first one and the most known is 1 or more points outside of control limits at 3 sigma. The second rule would be 2 out of 3 consecutive points outside of the 2 sigma warning limits, but still inside the control limits. The next rule would be 4 out of 5 consecutive points beyond the 1 sigma limits. And the last one would be 8 consecutive points beyond the 1 sigma limits. So for 1 or more points outside of the control limits, you have that the control limits are usually at 3 times sigma. And in that situation, the probability of x being less or larger than 3.0 or less than negative 3.0, that the probability of that is 0.00135. So the probability of either extreme, either to obtaining 1 point underneath negative 3 or above 3.0 is, as I mentioned before, 0.0027. And that would be the alpha, and 1 over 0.0027 would be computed as the average run length. For the cases of 2 out of 3 consecutive points, we would need to compute the probability in the region between 2 and 3 sigma, and then compute the binomial distribution for 2 out of 3 consecutive points. So you would have a probability of success associated to the area between 2 and 3 sigma limits and combinations of 2 out of 3. And now this could happen on the top side and this could happen in the bottom side. So whatever result you obtain there, you would have to multiply twice and that would give you an estimate of alpha for that particular rule. So in summary, for that second rule, what you do is you compute the probability of falling between 2 sigma and 3 sigma, and then that is your probability of success to the event of falling there. And now you use that as the P for a binomial distribution with 2 successes out of 3 attempts, and that would give you one-sided. Now you multiply that number times 2, because this could happen in the upper side or the bottom side. And finally, you add these two quantities, or you obtain the product of times 2. That would be alpha, and 1 over alpha would be the average long length. It's a similar process for the 4 out of 5 consecutive points beyond the 1 sigma limit. In this case, it would be the spaces between 1 and 3. And we also need to do the combinations or the binomial distribution of 4 out of 5 with this new probability. And the last one is 8 consecutive points on one side of the central line. For that, it'll be very easy. It's just 0.5. That's your chance to fall on either side, to the power of 8, and that would be falling one side. Now you multiply that number times 2. That would be the probability of this rule happening, because it happened either on the upper side or the lower side. And if that happens, it sends you the signal. So 1 over that probability would be the average wrong length associated to just that particular event. Of course, if you have all these rules implemented, we will need to go back to the multiple rules formula that we saw in the previous slide. Naturally, the most or the easier one to identify is when we are out of limits, out of the control limits, and for that, it is straightforward. You're going to find that there are different types of control charts. Basically, we have two types of control charts. We have control chart for variables and control charts for attributes. Variables are anything that you can actually measure as temperature or distance, anything that it has a continuous measuring condition. And the type of tables, the type of charts you can use are a combination of the X and the range, in which the range is used to compute the limits of the X bar chart, and we also need to keep track of the R on its own to measure the variability. Alternatively, if we have a more sophisticated personnel, we can compute the X sigma charts, in which instead of using the range particularly is very easy to use because it's just the largest number minus the smallest number. So you don't need to have a highly qualified people. Computing the standard deviation is more time consuming and it requires a better understanding of statistics. So, but if you have the ability to do that, you can still create the similar control chart for variables, in which now the pair is X sigma, and the limits for the X bar chart are dependent on the value of the standard deviation. Of course, we keep track of the standard deviation on its own in a sigma chart. Now you can see that all of these charts are either empirical or standard. Empirical means that we're going to use just the data that we obtain in our own measurements in order to build the upper limits and the lower limits and the central lines, both for X or for the range or for sigma. The standard means that if we have available a standard performance that we desire, or we think that the process should be capable of doing, maybe based on the fact that the vendors claim that that's what the equipment should be able to do, for instance, or that's what we are estimated as the average performance that we expect in order to have our cost as according to our standard cost, then we could use the standard mean for the numbers that we have for the variables, and the standard range, and the standard deviation. The other type of control charts that we have is control charts for attributes. Control charts for attributes do not actually measure quantities that are continuous, but we actually count, for instance, the number of nonconformities. The number of nonconformities in terms of the product means that we count how many defects we have in lots, and we have a proportion of defects that we are finding every time that we measure. We use that proportion as P. The alternative way to present the proportion is to actually count how many were the non-conforming in this particular instance, or making control charts for the number of non-conforming units in the sample process. That is very simple, because all we need to do is use that proportion of non-defectives times the sample size, and that would give us an expected value of non-conforming in every time that we do a sampling process. So the formulas are adjusted for either using P or NP in a very simple way. The next one is the C chart. The C chart counts the number of defects that happen per a certain number of events. It could be, for instance, the number of defects in 5 items. And similarly, we have the number of defects per item if we use just U. So we can use any one of these charts. The P and NP charts make the assumption of a binomial distribution. The C and U charts make the assumption of a Poisson process in which we count the number of defects per event. And that's why the formulas are slightly different. The formula handouts are on Blackboard, available for you. This is a summary for most of the formulas found in chapters 5, 6, and 7, and 8. At least the ones that you more likely be using in the test. Some of them, it may be that it's just a subtle difference, and I invite you to try to understand the formulas, because I'm not going to ask you to remember them, but it'll be easier for you to understand if you start to see where these formulas are coming from. In any case, the values for the parameters in the charts for variables depend on knowing other factors like A, B's, and D's. And we are going to just explain where to find them. When you have charts for variables, either XR or X sigma, you can obtain the values for the key parameters that you need to actually make the computations in the appendix number 6 on page 720, and that will give you the factors necessary to compute the charts for averages, chart for ranges, and the chart for standard deviations. The control charts for attributes do not require any of these special factors. We just use either the standard value or the sample value, that is the empirical value, for P, or number of or proportion of defectives, or the sample mean, or the expected number of defects in the case of the C and U charts. So there is no need for special tables, but you need the formulas that you can find either in the text or in the formula sheet. Finally, talking about the capability of the process, we have two measurements. We have CP and CPK. Those are very similar. CPK is a subset of CP. It's always CP is always smaller than CPK is always smaller than CP, and it's a relation between the actual variance of the process at the individual level. This is not the variance of the sampling process. That is, we're not canceling the variation due to the fact that we're computing averages. In other words, this is each individual product and its measurement. And that sigma is the complete range that we would expect to have in natural way for most of the observations. If the alpha associated to that is 0.0027, that means that the probability of falling within this sigma is 99.73. On the other hand, and that is the natural limits given the process as it is. On the other hand, we have in the numerator, we have the difference between the upper specification limit and the lower specification limit. And that is the range for which the product has an acceptance range. So in other words, if the space or the range that we call 6 times sigma is small compared to the range of the upper standard limit or specification limit minus the lower specification limit, if the 6 sigma is small, that means that this number should be larger, and hopefully larger than 1. And that would mean that the process has the natural capability to give 99.73 chances of being success, at least from the perspective of the width, because this does not talk about the mean. In other words, if the process is not centralized in the target, you can still have issues, but at least the variability of the process would allow you to obtain most of the product in good shape. Something that we need to stress is that CP is not a probability. CP is not the value of Z or C in the normal distribution. These are completely different concepts, and it is a proportion of how much the specification limits compare to the natural variation of the process. And it's not a probability, as I said, and I cannot count the measure just by looking at the number. I cannot count the measure of how many defects I will have just by looking at the CP. I would need to actually do the computations using a normal distribution, and for that matter, I still, with CP, do not have a centralized measure. That problem is solved with CPK. CPK uses the smallest of the two sides towards which the difference is. In other words, if the upper specification limit minus mu is smaller than the mu minus the lower specification limit, we are going to use the smallest of the two because that will be the most critical. And instead of using 6 sigma, we are going to use 3 sigma on either side. So now this is an actual measure of that compares not only the width of the range, but also compares the centralized performance of the process. And this again gives us an indication. If it's larger than 1, then we are doing all right, because in particular this measure gives us a key performance indicator. If this number CPK is larger than 1, that most of the product in a natural way would be in good shape, 99.73 or better. If the number is less than 1, then we may begin to have defective product. Now, as you know, the normal distribution is not a straight line function, so it is not going to be the same if you are just a few points below 1 as if you have several points below 1. The increment of the number of defective product will begin to accumulate faster. So this is a summary of this topic of control charts. I don't have a lot of computations. You have the examples on that in the textbook, and I gave you several problems to work with, and I hope that's sufficient for this week. But you know, you can get in touch with me, so please get in touch with me if you have any questions. Thank you.